Well, now we're going to be talking about comparing two population proportions, and we're going to use similar ideas to when we discussed comparing two population means. But now we're going to be dealing with instances in which we have categorical information. Okay, so this analysis is appropriate when there's a single qualitative or categorical response variable with a single characteristic of interest, and the treatment or input variable is also qualitative, okay, with exactly two levels. And this exactly two levels is very important. Now, we're going to compare the two population proportions and by testing hypotheses, and that's the main takeaway that I want you to have is testing hypotheses on two population proportions. I'll briefly mention how to calculate a confidence interval for the difference in population proportions. Now, when you're conducting tests of hypotheses for population proportions, the null hypothesis is always a statement of equality, just like before, and it says that the two population proportions are equal. And the alternative has one of the following forms. The one form is that one population proportion is greater than the other for the alternative, a statement of inequality. Or you could have that the alternative hypothesis is that the two are not equal and we don't know which one is greater. Okay. So if we're going to test proportions, we need a statistic. We're going to use the z statistic. And this is the statistics that we're going to use. Okay. Now, this uses a normal approximation, and it says that the mean is 0 and variance is 1, so a standard normal. Okay, that is how the z distribution has been used. And under the null hypothesis, P1 is equal to P2. Okay, so this difference is 0. It disappears down here. We also need to modify the denominator of this, and the denominator is modified in this way. Okay, it becomes the sample proportion because that's all that we have available to us. Okay, and this is multiplied by 1 over the sample size of the first group plus 1 over the sample size of the second group. And we use this statistic right here that's been highlighted to test hypotheses. Now I need to tell you how to calculate p hat because that's different than p1 hat. Okay. If you're going to use this normal approximation, you should ideally have the following situation. The sample should be independent, okay? So one treatment does not affect the other outcomes, okay? You need that the sample size, n1 times the sample portion P of population 1 times 1 minus p1 hat is at least 10. And the same requirement for the second population. Now, this p1 hat, that's the sample proportion for population 1. T1 is the total number of individuals in group 1 with the characteristic, and N1 is the total number of observations in group 1. Similarly, P2 hat is T2 divided by N2, and T2 is the total number of individuals in group 2 with the characteristic, and N2 is the sample size for population 2. Now, I talked about this p hat, that's important to calculate the standard deviation. That's just going to be the total in either population, T1 plus T2, that have the characteristic divided by the total sample size. Okay. And that is called the pooled proportion. Okay. So if I'm going to calculate a confidence interval, because this can be used to test hypotheses if the alternative is two-sided. This is the two-sided alternative right there. And only in this situation we can use the confidence interval. The confidence interval for a population proportion is going to be the difference in population proportions plus or minus the z alpha over 2 times this standard error right here. Okay, so let's now consider an example. Okay, and we have an experimental drug that's being developed. Okay, and the drug is tested at 2 different dosages, high and low. The researchers believe that a higher dosage leads to a higher proportion of individuals who experience side effects. We want to state the null and alternative hypothesis and test this claim at the 5% level of significance. So the null hypothesis is that the dose, the amount of drug that you take, doesn't matter. Okay? And for the population. The alternative hypothesis is that a higher proportion in the proportion of individuals who take a high dosage experience side effects in a higher proportion than the individuals with a low dosage. Okay, and let me fix this right now. Okay. So here's the data that we're going to use to test this hypothesis. This is the number of individuals experiencing side effects, 85. Here's the sample size. And for the low dosage, we have 950 people in that group, and 90 individuals experience side effects. Remember, it's not the number of people that we're comparing, but it's the proportion, the sample proportion. Notice that that's not listed until the end. The sample proportion is the number of individuals that experience the side effect divided by the sample size. So in this way, we're taking into account how many people are in the population that's being considered. So the sample proportion for the high dosage suggests is 14%, whereas the low dosage, even though it has a higher number, its proportion that experience side effects is only 9.5%. Okay, so does this mean that the two proportions of the populations are different, or are these differences due to random chance? Okay. So here is how we're going to test hypotheses. Notice that we have the criteria, that we have the normal approximation. We have that this is bigger than 10. N times P times 1 minus P is bigger than 10 in each group. Okay, so here's 77, here's 72. And the pooled sample proportion, the total number of individuals that experience side effects, is given by this quantity, and that's 11.2%. So now, if I want to calculate the p-value for this, I can go ahead and calculate the probability that the high minus the low, the observed sample difference, is bigger than the observed difference, which is 85 out of 600 minus 90 out of 700. And this is a standard normal distribution, so I replace that with z in the next line. This quantity, I go ahead and take the z-score. Okay. Now I subtract by 0 because that's the hypothesized sample difference. So I'm just taking the difference in observed proportions, that 85 over 600 minus 90 over 700. But here I'm dividing by the standard error. Okay, and I just used 0.11 instead of 0.112. Okay, and I divide by that quantity, and I get 2.84. I need to calculate the probability a standard normal is bigger than 2.84. So let's go to our list of calculators. Okay, let's go to the normal distribution. Okay, so mean 0, standard deviation 1, above 2.84, and let's calculate, that's 0.002. Okay, and we have 0.002, and so that's where we got that number. It's 0.2%. So we reject the null hypothesis because that's less than the significance level of 5%, and we reject it in favor of the alternative. In fact, we could reject this all the way up to 0.2% level of significance. Okay. So it is extremely unlikely that this difference is due to the random sample, and that is more likely that the difference is actually a difference in population proportions, that low dosages cause a lower rate of side effects in the population. Okay, so let's construct a confidence interval to determine how large this difference could be. Okay, and now that we've determined that they have a lower proportion, let's see by how much. Okay, so the confidence interval is given by this formula. Let's plug in the given numbers. We have P1 and P2, and so this is given by 0.14 minus 0.9, and we're going to calculate these numbers. The P1 is 0.14, I plug that in, N1 is 600, N2 is 950, and P2 is 0.09 or 9%. Okay. Now, you might be wondering, how did I get this 1.645? That came from the Z distribution. I want a 90% confidence interval, so let me go to the calculator for the inverse normal distribution. Okay, I want a 90% confidence interval, so that means 1 minus alpha needs to be 90%. Alpha is 10%, and so alpha over 2 is 5%. So 0.05, okay, is the area in the right tail, and I get this number, 1.645. That happens to be exactly the number I used. Okay, so Z alpha comes from that calculator. You can also use your table in the book, and it suggests the sample proportion could be as low as 0.018 or as high as 7.5% difference, okay, by going from low to high. Okay, that's all that I have for hypothesis testing on two population proportions. Thank you very much.